Hi, everybody. This is a refresher about the diffusion of pulmonary gases. We learned about this back in respiratory survey, but it bears doing a little bit of a refresher because after you guys come back from spring break, we're going to be talking about gas transportation and then acid-based balance. So I think it's just kind of a good idea to just make sure that we remember the things that kind of affect the diffusion of gases in our body and how gas moves from the lungs into the blood or from the blood into the lungs before we kind of get into those topics. Let's get my head out of the way here. All right. So again, just a reminder, the mechanics of ventilation only moves a bulk amount of air in and out of our lungs. So the next step of the process is respiration, which is the movement of gas across that AC membrane. Okay, so ventilation is just getting that air into the body. Respiration is moving that movement of gas across that AC membrane. Okay, so that process that takes place that allows for that movement of gas is called diffusion. So to fully appreciate diffusion, we have to understand a couple of those ideal gas laws. I know, everybody's favorite, ideal gas laws. So things like Dalton's law, which talks about the total partial pressures of a mixture of gases has to equal the sum. So that is that ideal gas law equation that we did, or not the ideal gas law equation, but the equation that we did in a survey that calculated out for the P big AO2 relates to Dalton's law. So the alveolar gas, partial alveolar gas equation. And then you need to kind of understand, kind of how those partial pressures of gas work with, against what kind of makes up that atmospheric gas that we breathe in, understanding some fundamental difference between pressure gradients and diffusion gradients, okay? So this pressure gradients is what moves that gas in and out of the lungs. Those diffusion gradients are what we talk about when we're moving the gases across the AC membrane. So those are, it's still a gradient, still works the same as a gradient where you're moving from high to low, but, we talk about diffusion gradients with respiration, pressure gradients with ventilation. So Dalton's law. So Dalton's law is the law of partial pressure. So that just means that the total pressure exerted on a mixture is going to be equal to the sum of the pressures exerted independently by each of those gases. So if atmospheric gas is made up of oxygen, nitrogen, carbon dioxide, and then those are the kind of the three main ones. Each of those partial pressures of gas is going to total the entire atmospheric pressure, right? So atmospheric pressure at sea level is 760. All three of those gases have to add, partial pressures of those gases have to add up to be 760. So this just kind of gives an example of that. So gas A has a partial pressure of 10. Gas B has a partial pressure of 5. So A and B, that mixture, has to be those two added together. It's very simple, right? Everything has to add up to the total partial pressure. Okay. So again, why is this important to us? It's just to understand that partial pressures of atmospheric gases are usually made up by that nitrogen, oxygen, and carbon dioxide. And then there's a few that makes up less than 1% trace gases like argon and radon, things like that. So these partial pressures aren't going to change. So if I climb Mount Everest, there's still going to be 21% of gas, the percentage doesn't change. So if I climb Mount Everest, 21% of the gas mixture is going to be made up of oxygen, just like it is at sea level, but those partial pressure changes because the amount of gas, if you think about all those gas molecules weighing down on us at Mount Everest when we're really, really high up in the air, there's less gas molecules up there to weigh down on us, but as we go close to the sea level, we have a lot more pressure, a lot more molecules that are sitting on top of us, creating that pressure. So, because that partial pressure is made up by the amount of concentration, it's going to be kind of relative to that barometric pressure. So we can easily determine what the partial pressure of each of those gases are if we know the concentration. So we did this again last semester, but given an example, at sea level, where the barometric pressure is 760, and our concentration of oxygen is 21%, then my partial pressure of oxygen can be calculated out to about 159.6. Okay, so all of those partial pressures have to collectively add up to whatever the barometric pressure is at that point. So if you're given the barometric pressure at sea level of 760, all of those partial pressures have to add up to be 760. Okay, so this is just kind of an image from the text that just talks about the atmospheric pressure, and about 78% of it is made up of nitrogen. So that means the partial pressure of nitrogen at sea level is going to be about 593. Our partial pressure of oxygen is about 21%, given that means our partial pressure of oxygen at sea level is about 160. And then we have our partial pressure of CO2 and kind of the other gases that make up the rest. Okay, so if you think about it as, all of the molecules sitting on top of you, if we're closer to the surface, so we're higher up, we're going to have less molecules sitting on top of us. So atmospheric pressure decreases as the altitude increases. So as we go up in altitude, that partial pressure decreases due to the density of the gas that's sitting around us. The density of atmospheric gases decreases, then the partial pressure also decreases. So if we would calculate that out, so if we look at this one here, and we think about the percentage of oxygen always being 21%, both at sea level and the top of Mount Everest, then when we calculate out the partial pressures, so if I would calculate out the partial pressures of both of these, let's say at Mount Everest, I have a partial pressure of, instead of 760, excuse me. All right. So the barometric pressure, let's say the barometric pressure on top of Mount Everest is around 270. Okay. Just need to change my pointer thing. So if my barometric pressure is 270 on top of Mount Everest and 760 at sea level, if I multiply each by 0.21 for 21% oxygen concentration, you will see how people that are climbing mountains can have effects on their oxygenation, not by the change of the oxygen concentration, but just by the change of those pressures. So now I only have a barometric or a partial pressure of oxygen of 56.7 versus like the 159.6 that you get at sea level. So that's like a third of the partial pressure of oxygen when you go from like Miami, Florida, all the way up to the top of Mount Everest. So that can severely affect patients' ability to oxygenate. Okay, let's okay. So if you think about partial pressure of oxygen when you're going below sea level, this is like kind of the theory behind hyperbaric chambers and oxygen in hyperbaric chambers. So as atmospheric pressure increases by 1 atmosphere for every 33 meters below the descent of water. So every 33 feet you go below the surface of the water or sea level, then you're adding an entire other atmosphere. Okay, so that's quite a bit of pressure. All right, so that additional partial pressure, that is going to increase the partial pressure of the oxygen. So in hyperbaric chambers, typically what we do is we increase the partial pressure or the barometric pressure around the patient. So when we're increasing that barometric pressure by like 1 to 3 atmospheres, we're also greatly increasing the amount of partial pressure of oxygen that the patient's receiving, which can help with things like diabetic ulcers, wound healing, also can help with some other types of treatments that patients receive. Oops, going back a little bit. All right, so remember, with pressure gradients, movement of gas is going to be from areas of high concentration to areas of low concentration. This is how we get air in and out of our body. And individual gases are going to move in the same direction, so in and out of the lungs. So gas diffusion is the movement of individual gas molecules of those areas of high concentration to areas of low concentration. So these individual gases are going to move independently from other gases from areas of high or low concentration. So that's an important distinction, because if you think about it, two different gases can move or diffuse in opposite directions. All right, so if you think about those alveoli again in our lungs, oops, I keep missing my little pointer here. So if you think about my alveoli and my capillary bed here, so as the blood is coming into the lungs through this capillary bed, it's got a lot of CO2 in it. Okay, this has high concentrations of CO2 and low concentrations of oxygen. But as it comes in contact with the alveoli, there's high concentrations of oxygen here. So then diffusion is going to happen this way for the O2. O2 is going to diffuse across the AC membrane into the blood, and CO2 is going to diffuse across the AC membrane into the alveoli. Okay, so this is going to keep happening until you see, until you see the diffusion or those partial pressures equalize. So once my CO2 in my blood matches the amount of CO2 in my alveoli, that diffusion is going to stop. Once the diffusion of oxygen is the same across both, so alveolar oxygen, I'm going to type this because I cannot write very well. So once my P big A, which is the alveolar O2, is equal to my P little a, which is my arterial O2, diffusion stops. And again, the diffusion works opposite for CO2. So once my P little a CO2 is going to be equal to my P big A CO2, diffusion of CO2 is going to stop. Okay. So this chart just talks about the partial pressures of gases in both the atmospheric air into your alveoli, and then into your arterial blood, and then your venous blood. So obviously this is the air we breathe in. That's why my partial pressure of O2 is about that 159 that we've talked about how you calculate. My alveolar gas O2 though is less. And why is that? Hopefully everybody remembers that has to do with the fact that you have this partial pressure of water vapor, right? So that water vapor, as we heat and humidify the gases that travel down into our lungs, that water vapor is going to affect the total amount of O2 that you can, partial pressure of the total amount of O2, right? Because water vapor is a molecule, so it subtracts from that gas mixture or adds to that gas mixture. Okay. Then it gets into the arterial blood, gets dropped off at the tissues then by the arterial blood, and then comes back to the lungs where we're deoxygenated with our blood, venous blood, and our venous blood has more CO2 because it picks up the CO2 from the tissues. Okay. So there is a relationship between temperature, humidity, and water vapor pressure. Okay, so for your kind of knowledge, for all the calculations that we do with our arterial O2 and how to calculate that out, we're assuming that we're at kind of normal body temperature, 100% relative humidity, which would be that 37 degrees Celsius. Okay, but if our patients are hypothermic, then they are going to have less water vapor in their lungs or in that oxygen air mixture. Okay, so that table, before we talked about how the atmospheric air PaO2 is at 159, and that's a lot higher than your alveolar PaO2, and that's because, again, you have the carbon dioxide, a much higher level of carbon dioxide in your lungs, and a much higher level of water vapor in your lungs. Okay. So again, water vapor is considered molecular water, so that is going to be part of that total partial pressure, or has to be factored into that total partial pressure. Okay, so reminders about humidity and water vapor. Water vapor, like I said, has at 37 degrees Celsius, which is our body temperature, has a relative humidity of 44 milligrams per liter of water. So this is the actual amount of water that we can carry, max capacity. And then relative humidity would mean if we were at 100%, then the actual content would be 44 and the max capacity would be 44, giving us 100%. Humidity deficit is when the actual content isn't going to equal our max capacity. Okay, not that big of a deal for you guys to remember for diffusion, but something that you kind of just a refresher about humidification from Therapeutics 1. Okay, so all of that is a big lead up to this ideal alveolar gas equation. So this is how we calculate out the amount of oxygen that actually got into the alveoli during ventilation. Okay, so this calculation, again, when you're looking at calculations for respiratory therapy, that large A, the capital A, signifies alveoli content versus the little a is arterial content. Okay. All right. So when you're trying to calculate out the amount of gas, ventilation, oxygenation that got into our lungs, we're going to be taking the barometric pressure, all right, because that should be the total pressure, minus the water vapor. And then we can multiply by the concentration of oxygen. So we have to get rid of the water vapor first, and then calculate out, multiply by the actual oxygen concentration that got in there, so your FiO2. Then you can subtract by the PaCO2, and I like to do that by multiplied by 1.25. I prefer to do it, remember it that way rather than memorizing it, dividing by 0.8, but to each their own, either way. So remember, you're only going to use this kind of coefficient or whenever your oxygen concentration is less than 60%. Okay, so let's show you an example of this. So if a patient's receiving an FiO2 of 40% on a day when the barometric pressure is 55 and the PaCO2 is 55, what is their alveolar oxygen tension? So you plug in your numbers, barometric pressure of 755 minus 47. Okay, so you're always going to use 47 for your partial pressure of O2 in the lungs. That gives you 708. You can multiply that by 0.4, which is our FiO2, or 40%. And then you're going to subtract 55 times 1.25, which is 68.75. So this gives you 283.5 minus 68.75, or a partial pressure of 214.45. Okay. So if you think about this equation, or you think about this mathematically, in order to increase the partial pressure of oxygen in my alveoli, thus increasing the likelihood that it's going to diffuse, right? Because that's going to increase my pressure gradient. I could either increase the barometric pressure, which is what we do with hyperbaric, or I could increase the concentration of oxygen. Okay, those are going to be the two things that I can control and help improve my patient's oxygenation. Okay, so like I said before, clinically, when the PaCO or PaCO2 is less than 60, or when the patient is receiving oxygen greater than 61% or greater, then you're going to simplify the equation by removing that 1.25. So talking about the diffusion of gases, that first part of the conversation is just kind of talking about the diffusion gradient. So by increasing my P big AO2, my partial pressure of oxygen in the alveoli, that is going to encourage it to diffuse across the AC membrane into my arterioles. Okay, so that is that diffusion gradient. But there's other things that are going to affect this. So that major barrier those gas molecules have to diffuse across is that AC membrane. Okay, so it's that arterial or alveolar capillary membrane. Okay, so you've got kind of this membrane or interstitial space that has to go through, and then these base membranes. So this membrane should be very, very, very thin, like 2.5 microns thick at the most. Okay. So typically, if it's, a normal thickness, normal gas pressure of the O2 and the CO2 are going to cause that movement through that AC membrane. Okay. Typically, diffusion should only take a quarter of a second to happen. So very, very, very quickly. And the blood is going to be moving past those alveoli at a slower rate of about 3/4 of a second. So plenty of time for diffusion to take place. Okay. But during things like exercise or stress, our blood might start moving through that capillary bed at a faster rate. That's why, we try to breathe faster. We try to, when our heart rate increases when we're exercising, but also that diffusion or that perfusion to the lungs is also going to increase. So the blood's moving through our lungs much, much quicker. So we will not have as long, we don't have 3 times the amount of time that we need for diffusion. It might be a 1-to-1 or 1-to-2, which in most healthy adults isn't going to be a problem, right? Most of us, hopefully all of us can go for a run or go for a walk or a run or a bike ride without being desaturating or having low oxygen levels. But if our rate of diffusion decreases because of things like alveolar thickening or usually it's alveolar thickening, then that oxygen equilibrium or the diffusion across that membrane, it will probably not likely happen. Okay, so this brings us back to Fick's law. So Fick's law was what we learned about last semester, that talks about the things that are going to affect the rate of diffusion. So V over here represents diffusion. A is our alveolar surface area. So how much of our alveolar membrane or how many alveolars we have in our lungs or our body. D is that diffusion coefficient. That's going to be the same for all of our patients because it's a diffusion coefficient for oxygen. That P1 minus P2 is that pressure gradient created by the partial pressure of oxygen in our lungs versus the partial pressure of oxygen in our alveoli. And then T is that thickness of the wall, alveolar wall. So this is just kind of a picture representing each of these factors. So I kind of like this picture because it kind of shows you what kind of in a real scenario, how these things are going to affect that movement of the gas. Okay. So another thing that's going to kind of affect our diffusion or how much oxygen can be in our blood and how much CO2 is in our blood is Henry's law. So that is talking about the amount of gas that dissolves in a liquid at a given temperature. Okay, so the amount of gas that dissolves in a liquid is going to be proportional to the partial pressure of the gas. So know that carbon dioxide is quite a bit more soluble than oxygen. So it's going to have a more partial pressure than the oxygen does. Graham's law talks about the rate of diffusion of gases through a liquid. So that's going to be proportional to that solubility coefficient. So Henry and Graham's law kind of work side by side when we're talking about diffusion of gases into the blood. So it's going to also be inversely proportional to the square root of the gram weight. So diffusion is going to increase when it becomes more soluble, is what this is saying, and it's going to decrease based on how large the molecule is. So again, your diffusion rate for carbon dioxide is going to be quite a bit. Diffusion rate for carbon dioxide then becomes quite a bit quicker for CO2 than it does for O2. So just to summarize again, by combining these, then your diffusion of two gases is going to be proportional to the ratio of their solubility coefficients, inversely proportional to the ratio of their molecular weights. And then that's the equation down below. That's the combination equation. So don't worry about the math as much. Just remember that CO2 is going to diffuse about 20 times faster than O2 because of these factors. Okay. So when we talk about diffusion of gases, you have to have ventilation and you have to have perfusion to have this happen, right? You need to have oxygen coming in to the alveoli and blood passing by that alveoli to have something for the gas to diffuse into. So when we talk about being perfusion limited, means the transfer of gas across the alveolar wall is going to be the function of the amount of blood that flows past the alveoli. So if I don't have blood for the oxygen to diffuse into, I won't have diffusion. Okay. So nitrous oxide is a anesthetic gas that is mentioned in one of the clinical connections of your textbook. It's just worth talking about a little bit because, it's very popular to use for general anesthetics because it diffuses quickly across that membrane. So it gets into the blood flow and gets out to the body and causes its kind of anesthetizing effects. And it's also, because it diffuses back quickly, it kind of is removed from our body quickly afterwards. Patients kind of wake up from it, don't suffer like long-term effects of that general surgery as much. But if you have patients that have diffusion issues like COPD, things like that, this can be a complication that anesthesia providers need to be aware of when considering using it. Okay. So when we talk about like perfusion limited diffusion issues, you think about things that are going to diseases that would cause perfusion limited diffusion issues would be diseases that affect the blood flow to the lungs. So anything like a PE or pulmonary embolism is going to limit the amount of blood flow to the lungs. That's going to help it, diffusion take place. And then gas flow limited diffusion issues would be more. Gas flow limited diffusion issues would have to do with the movement of gas through that alveolar wall. So these would be more of our respiratory diseases. So a common one would be like emphysema or pulmonary fibrosis that is going to affect that AC membrane, that alveolar surface area or alveolar thickness. So another gas that's worth noting, talking about during diffusion, is carbon monoxide and hemoglobin. So carbon monoxide is going to be something that rapidly bonds with hemoglobin and then doesn't generate much partial pressure in the plasma. So again, anything that's going to exert partial pressure is something that's dissolved in the plasma, like the oxygen or carbon dioxide. But if it's bound to hemoglobin, it's not going to be exerting that partial pressure. So that's why you could have a large amount of carbon monoxide buildup in the blood, because it's going to bind up with that hemoglobin, plus it's going to have the ability to dissolve in that plasma for extra carrying capacity, and that's going to affect our tissue hypoxia. All right, so perfusion limited diffusion or ventilation limited issues with diffusion, this all relates to what we learned about last semester with our VQ matching, so ventilation perfusion matching. If you have too much ventilation not coming into contact with blood flow, that is considered wasted ventilation or dead space ventilation. Okay, if you have a decreased VQ matching, that's when you have too much perfusion but not enough ventilation, and then that's wasted perfusion. So that blood is getting shunted, or you're hoping that blood starts getting shunted away from areas that are not getting ventilated. That's what we talked about last chapter when we talked about that increase in pulmonary vascular resistance that our bodies kind of have built in when you're oxygen levels in your blood gets too low, because we don't want to waste that perfusion with alveoli that aren't being ventilated properly. Okay. So pulmonary edema is going to also cause, we talked about a little bit about ventilation issues with asthma, or not asthma, excuse me, emphysema and pulmonary fibrosis. Emphysema mainly increases your diffusion or decreases diffusion because so emphysema increases or decreases your diffusion because of your alveolar surface area is decreased. Pulmonary fibrosis is going to increase that alveolar wall thickness, and pulmonary edema, which is going to include that interstitial edema and fluid going into that through that alveolar interstitium and causing excessive amounts of fluid in the alveoli, is also going to affect our ventilation and diffusion because of that increase in that wall thickness. So factors that are kind of affect the amount of diffusion that's happening in our lungs. So the tests that we perform on patients that measure their diffusion is called a DLCO test. It's looking at, because carbon monoxide really is readily picked up by the blood. It's a really good diffusion limited gas that gives us a good idea of how well gases are moving across that AC membrane. So we perform this test in the pulmonary function labs, where patients are going to be asked to breathe in to total or full inspiratory capacity, a breath of carbon monoxide, then exhale it as much as they can. And then we are going to look at how much they breathed in, how much they breathed out, and we can calculate how much diffusion took place. So a couple factors that are going to affect the measured diffusion level is going to be age. So that DLCO is going to change with age. So usually it's going to increase up to the age of 20, and then after 20 it's going to start decreasing, just because we have reduced alveolar surface area as we age. Lung volumes, if I can't take as large of a breath in, that is going to affect how much diffusion happens, because ventilation is going to affect diffusion. We talked about that. So the greater the ventilation, the greater the size of the breath, the greater the amount of diffusion. Body size, so typically that DLCO level is going to increase with body size, and again, ideal body size, because then our lungs are bigger. Body position, so if we typically have better diffusion DLCO levels when we're in like the supine position compared to upright, and that has to do with the amount of perfusion to our lungs. Exercise is going to increase your DLCO because of that increased cardiac output. Increased alveolar oxygen partial pressure, because that increases that pressure gradient. More hemoglobin. If our hemoglobin level is high, then it binds to the hemoglobin. Thus, we'll have a higher carrying capacity and a higher diffusion rate. And then carboxyhemoglobinemia, that happens when patients already have that carbon monoxide bound to their hemoglobin. This decreases the pressure gradient and then reduces that DLCO level. All right, so just again, how oxygen can be perfusion or diffusion limited. So under normal resting condition, diffusion of oxygen is going to be perfusion limited. So the transfer of gas across that AC membrane is going to be dependent on the amount of blood that's flowing past those alveoli. Okay, so typically we're going to be perfusion limited. That's usually what happens in the lungs with diffusion, but it can be limited by diffusion, and that is going to be any factor that are going to increase the thickness of that AC membrane. So pulmonary edema, pulmonary fibrosis, or any disease that destroys that alveolar surface area or decreases alveolar surface area, like emphysema.